Thank you very much. First of all, Happy New Year and welcome back to our quantum seminar series. Today we are welcoming Professor Stefan Willitsch from the University of Basel. Just a short introduction. He got his PhD from in Department of Chemistry at the Eidgenössische Technische Hochschule in Zurich in 2004. And he got then a junior research fellow at the Christchurch and Physical Theoretical Chemistry Lab at the University of Oxford. And then after a few years, he became a lecturer in physical chemistry at the University of College London in the UK. And then he got an appointment as a Swiss National Science Foundation professor at the Department of Chemistry at the University of Basel. In 2014, he became associate professor at the same department. He got many awards, like the Marlowe Medal of the Royal Society of Chemistry, and for instance, the Ruzica Prize, to mention a few. I don't want to go all the awards he mentioned here in his CV on the net. But I would like to introduce the topic he is going to talk to us today, which is the quantum technologies for molecular precision spectroscopy. Professor Willitsch, you are welcome, and we are here to listen to your talk. Please.
Okay. Thank you very much for the kind introduction, and indeed also for the kind invitation. And I'd also like to wish everyone a happy and particularly healthy New Year on this occasion. It's a great pleasure to be here today and be able to present some of our recent work to you. I should already start with a disclaimer. I was also asked to talk on this topic on the recent ECTI conference. So if the ion trappers among you have maybe already heard at least parts of the story, I already apologize, but I tried to put some different focus on parts of the talk, so that at least those who have already heard me actually also hear something new here. Okay, so the title of my talk is Quantum Technologies for Molecular Precision Spectroscopy. And as has already been mentioned, I'm part of a chemistry department, but what we essentially do is molecular physics. And one of our areas of activity is high resolution and precision spectroscopic measurements. And in this context, we have been developing new quantum techniques over the last couple of years with the aim to do extremely precise spectroscopic measurements on molecular ions in the end. And so I will start my talk with a short motivation on why we want to achieve quantum control of single trapped molecules and molecular ions in our case. And in order to contrast the new methods that we have been developing for this purpose recently, I'd then like to contrast it how measurements on molecular ions have been done in the past by us and then by the entire community actually. And then I would introduce our new method. It's a quantum non-demolition state readout method, which uses coherent motion excitations of the ion in the trap, in contrast to what has been done before. I will then discuss how we want to use this to study clock transitions and by the same token also qubits in our PET molecule. This is the nitrogen molecular ion. And then I will also discuss about a recent development that we have here in Switzerland, a frequency transfer network that we and many others in this country will then intend to use for precision spectroscopic measurements. And I will then finish with a summary and some conclusions. Okay, so let me start with a short motivation why we want to control trapped molecular ions on the quantum level. As I've already said, so our main motivation is applications in precision spectroscopy. And that again can then be used for thinking of building new types of clocks based on molecules, to test fundamental physical concepts with precise spectroscopic measurements. Of course, molecular qubits are also an application that one can think about here. And then in a completely different context, all these developments are also quite interesting in the realm of collision physics and maybe even chemistry. So very precise spectroscopic measurements are these days mostly performed on atomic systems, using very sophisticated experimental techniques that also connect very much to recent developments in the world of quantum science. And it's only natural to try to adapt these sort of techniques also for molecular systems. And we and many other groups in this community have been working on this for quite some time. However, when dealing with molecules, there are a range of challenges that one has to face in comparison to atomic systems. And all of them essentially boil down to the vastly increased complexity of molecules compared to atoms. And to give you an illustration, I mean, what I show here on the right-hand side is a schematic and a small excerpt of the energy level diagram of our favorite molecule, N2+. And I mean, in atoms, you're used to electronic motion, you're used to spin degrees of freedom, and then you're used to Zeeman degrees of freedom. And in molecules, you have all that, of course, but then, of course, you have also the different nuclear degrees of freedom. You have vibrations, you have rotations, you have coupling between all of them. And so this gives rise to a very rich energy level structure that we somehow need to be able to cope with and control. So that makes certain tasks that one needs to do in these sort of experiments quite challenging. It starts with internal state preparation, right? So every, respect to the quantum protocol requires that your quantum system is initialized in a well-defined state. That becomes already quite tricky with molecules. Then translational cooling, which is the working horse of atomic physics, also becomes quite tricky here, because the vast majority of molecular systems cannot be laser cooled, because most molecules just do not have closed optical cycling transitions. Some do, and there are great experiments that are currently being done on those systems, but most molecules, including N2+, don't have this. Then, for the same reason, because there are mostly no closed optical cycling transitions, state detection becomes very, very difficult, right? I mean, in experiments with atoms, right, you use readout on an optical cycling transition in the end to detect the outcome of your experiments. Can't do this with molecules if there are no optical cycling transitions. And also all sorts of coherent manipulations that you want to do also become much more challenging because of this increased complexity of the energy level structure. So in my group, we have been working on tackling all of these issues for a decade now or so. And I should also point out that we are not the only ones when it comes to doing these experiments with molecular ions or doing these developments with molecular ions. There is an ever-growing number of groups who are involved in this community. And it has been quite a rapidly growing field over the last few years. Okay, so let me set the stage now with our favorite molecule. So one advantage of molecules, right, compared to atoms, that immediately comes to one's mind is their sheer diversity, right? So with atoms, you have only so many systems at your disposal with which you can do something. With molecules, there are billions and billions and billions. And so depending on what sort of application you're interested in, right, you have the liberty to pick your favorite molecule. And our favorite molecule is N2+, the nitrogen molecular ion. And we have picked it because it's a symmetric homonuclear molecule. So that means is that it has no permanent dipole moment. And that entails that rotational and vibrational spectroscopic transitions are electric dipole forbidden. So these transitions become allowed in the higher approximations, like electric quadrupole and the magnetic dipole, but those are very, very weak compared to the electric dipole transitions. So, that means that we have very narrow transitions, right, which are in principle quite interesting for precise spectroscopic measurements. So also because it has no permanent dipole moment, we have very small systematic shifts on, or many of the systematic shifts that one needs to worry about are very small when it comes to rotation and rotational transitions, which is also an important feature for precision spectroscopy. And because it doesn't couple easily to the radiation field, there's no redistribution of the state populations because of coupling to ambient black body radiation, right? That is maybe a more technical issue, but for trapped ion experiments, a quite important one. And what's also nice is that at least in the rotational ground state of the molecule, we have the choice between two nuclear spin isomers, one with total nuclear spin equals 0 and one with total nuclear spin equals 2. So this means that you can either have or have not hyperfine structure, right? And both scenarios can have their advantages and disadvantages. So Endtoplus has been looked at quite in some detail theoretically in recent years. It has been proposed as a system to study a possible time variation of the proton to electron mass ratio. Molecules like Endtoplus have also been discussed in terms of developing new molecular clocks. So these are also the kind of reasons why we are particularly interested in this system. Okay, so before I show you some results, let me say a few words about the experiment. So my former postdoc, Sif Meir, liked to call it an ion trap quantum computer coupled to a molecular beam machine, which is a very picturesque description of what it is, but it's not too far off the truth. The heart of the experiment is a linear quadrupole ion trap, which are similar to the ones which are used in many ion trap quantum information experiments, like the ones you do in Mainz, for instance. And here, this is really the heart of the experiment. Here we trap the ions, here we cool them, and here in the end manipulate and study them. And what we usually have are two ion crystals consisting of a single calcium ion, and then one nitrogen ion, which is then sympathetically cooled by the calcium ion in the trap. So this experiment is coupled to a molecular beam machine, and this molecular beam machine introduces a beam of nitrogen molecules into the experiment, from which we then generate the molecular ions by photoionization. So, and we have a range of lasers that interface with this experiment. We have lasers for the ionization of the calcium atoms and the nitrogen molecules. We have lasers for the cooling of the calcium ions. We then have lasers for the coherent manipulation of the molecules, which is what I'll come to later. And then all of this is then, we have also infrared lasers for infrared spectroscopy, which we are ultimately interested in. And then we also, this is all coupled to or locked to a frequency comp, which is then also stabilized by a primary frequency standard, as I will explain later on. Okay, so let me walk you now a few key techniques that we use in our experiment. And one problem that one faces immediately when dealing with molecular ions is one needs to generate them, right? And one needs to initialize them in a well-defined internal quantum state. And that's a problem that has ravaged the field for quite a long time. I would say it has now been solved by various methods already 10 years ago. And for our case, for homonuclear diatomic ions, the method we adopted to do this is state-selective threshold photoionization. So the idea behind this method is the following. The ions are generated by photoionization from their neutral precursor molecules. But if you do the ionization in a clever way, then you can tailor the process such that the ions are already produced in a well-defined rotational and vibrational quantum state. So the state preparation is already taken care of during the generation of the ions. And this scheme essentially relies on using photoionization selection and propensity rules together with energetic constraints to drive the photoionization process in the desired way. And in this way, we can produce the molecular ions in the rotational ground state or selected rotationally excited state. So what we then typically get in the experiment, this is shown here. What you see here, this is a fluorescence image of a Coulomb crystal of laser-cooled calcium ions in our ion trap. And in the center of this Coulomb crystal, you see a region where the fluorescence has disappeared. And this is where molecular ions have been sympathetically cooled into the crystal. We can't laser cool the ions directly because they don't have any optical cycling transitions. So what we do is we trap them together with laser cooled atomic ions, calcium plus in this case, and through collisions between the two ion species, energy is removed from the nitrogen ions by the calcium ions, and from there it's ultimately removed by the laser cooling. So in the end, what we get are these molecular Coulomb crystals, as we call them, where we have ordered structures of ions in the trap that consists of both species of the calcium ions and the nitrogen ions. Okay.
May I ask one quick question?
Yes, sure.
Do you lose the ions due to charge exchange reactions or not?
Yeah, that's a good point. Not in our case. Charge exchange is not an issue, but actually the lifetime of the ions of the molecular ions in our experiment is limited by their chemical lifetime. They do react with residual hydrogen gas in the background vacuum, and so depending on how good this vacuum is, yeah, that ultimately determines the lifetime of the nitrogen ions. Yeah, but as a matter of fact, this is the process that limits at the moment the duration of our experiments. Yeah.
And what kind of simulation are those?
So at the bottom, what you see here, this is a molecular dynamic simulation of this Coulomb crystal here. So it's essentially what we do here is we solve the classical equations of motions of these two ion species in the trap under the influence of the laser cooling. And by comparing the experiment with the simulation, one can then work out, things like number of ions and the secular temperature of the ions in this trap. And what one can also do in the simulations, of course, as it is done here, one can make the molecular ions artificially visible, right? Because in the experiment, one doesn't see them because they don't fluoresce. Yeah. But by carefully comparing the two, right? I mean, you can immediately say, okay, we have a molecular ion here, we have one here, we have one here, and so forth. Yeah. So this is a general purpose tool which we do to analyze the fluorescence images that we get from our experiments. Okay, so in the past, we and also the entire field essentially have done more or less used chemical detection, right, to determine the outcome of spectroscopic experiments on these on these trapped molecular ions. And there are different flavors of this. What we have adopted is so-called a laser-induced charge transfer. So here comes a charge transfer now, but a deliberate charge transfer in order to detect spectroscopic excitations. And this scheme relies on the following idea, which is actually an old trick in the book of chemical physics. Namely, it has been known for a long time that nitrogen ions can undergo charge transfer with argon atoms, but only if the nitrogen atoms are vibrationally excited. And the reason is a slight mismatch in the ionization energies between nitrogen and argon. So this charge transfer process is energetically not possible if the nitrogen is in the vibrational ground state. So this means that if you excite the nitrogen ions to the vibrationally excited state with a laser, then you can detect this excitation by this charge transfer reaction. Yeah, and that is what we have been doing in the past for nitrogen. And as a matter of fact, this is what we have been doing in order to study the infrared spectrum of nitrogen. As I've already said, it doesn't have a dipole allowed infrared spectrum. It's only quadrupole allowed, or in some cases even magnetic dipole allowed. But the oscillator strengths for these transitions, they are very, very small. So to give you an idea, so the first vibration excited state of N2+ has a radiative lifetime of 160 days. Yeah, so we're talking about half a year. So that translates into a natural line with on the order of 10 nanograms. So that's 10 orders of magnitude weaker, right, than any decently dipole allowed infrared transition in a polar molecule. So these transitions are really insanely weak and therefore also very narrow. So what we have done already a couple of years ago, we have used a quantum cascade laser to irradiate specific rotational hyperfine components of these vibrational transitions and then study them. And then we were detecting these excitations via this laser-induced charge transfer scheme. And in the experiment, this looked like this. So one needs now to have a very sharp eye to see this. So in the experiment, we would have a Coulomb crystal like this before this laser excitation, and then we would do this infrared laser excitation and then admit the argon atoms, perform this laser-induced charge transfer, wait until the nitrogen ions have reacted away. And then one would see that this central part of the crystal slightly changes because of the disappearance of the nitrogen ions from this crystal. And by the rate of the disappearance, we can then work back essentially absorption strengths on these infrared transitions. And that allowed us to record an excerpt of the infrared spectrum of the nitrogen ion, to the best of our knowledge at the time, which is already 7 years ago now. This was the first infrared spectrum of a first quadrupole allowed infrared spectrum of a molecular ion that had been recorded at this point. These transitions are so weak, it took us a year to find them. Yeah. And then it took us half a year to take these data. Yeah. So we were very proud when we got these results. But if you look at the spectrum, you can also see the problems here, right? I mean, in spite of the great effort we have taken to get this spectrum, the signal to noise ratio is very poor, right? And moreover, if it takes you half a year, right? I mean, to get a spectrum like this, yeah, I mean, this is not the way forward to do precise spectroscopic measurements. So it was clear to us that we had to do something, right? We need to become much more sensitive than we are in these experiments. Okay, and then there are several ways how you can approach this. You can say, okay, I mean, you have been using here very few ions, right? On the order of 20, 30, use more. Okay, increase statistics.
Sorry, a good question. This is nowhere close to nanohertz, right? This is 10 to minus 3.
Very good. Yeah.
So
exactly.
what is the mechanism?
Exactly, yeah. So here we were actually limited by the bandwidth of the laser. Yeah. So so we are nowhere near close to the natural line width here. So we were using at that time a quantum cascade laser that had a line width on the order of a couple of megahertz, and this is what we see here in the spectrum. Yeah. So this is by no means what I would call a precision spectroscopic measurement, neither in terms of the line width nor in terms of the sensitivity. Yeah. And that is exactly the problem here. So we had to do something. And so our solution to this problem was actually not to use more ions, yeah, to increase the statistics, but the solution was to use fewer ions. Yeah. In fact, only one. But now do the experiment in a way in which we do not destroy the ions anymore, because the destruction of these ions was in the end a big problem, right? After the measurement, the ions were chemically destroyed. So we had to reload them, go through the entire procedure again. So in one experimental cycle, in doing that took about 15 minutes. Yeah, and that was just too long. So what we decided to do is we would revert to a single ion, right? And do the experiment on this single ion over and over again with a very fast cycle in a way in which we would not destroy the ion chemically, and moreover, even not even destroy its quantum state. So what we came up with is a quantum non-demolition scheme to read out the state of a single molecular ion in the trap, which relies on a coherent motional excitation of these ions in the trap. And what this did in the end, so it improved the duty cycle by 5 orders of magnitude. Yeah. So what would take 15 minutes, yeah, now takes 30 milliseconds. And it also removes ensemble averaging, right? Because we're only using a single ion, which is also nice in terms of doing precise spectroscopic measurements. So what we adapted here for molecules is, if you like, a variant of quantum logic spectroscopy that has been done for atomic ions in various guises. Our scheme has been inspired by an experiment on the aluminium ion by the NIST group already 10 years ago. So we developed an adaptation for this for molecules. And I should also say that similar schemes and similar type of experiments are also done by other groups, for instance, by Pete Schmidt at PTV, or James Chow and Didi Leifried and NIST, and Michael Drewsen and Aarhus, and also many others are working on this. So we are by no means the only ones who work in this field. So now let me walk you through how we do these experiments, and also to give you an impression of how they contrast to everything that we have done before. So instead of a big Coulomb crystal, we now use a calcium nitrogen 2 ion string, like the one here. I've already shown this on the previous slide. So there's a single calcium ion in the trap. Here you see or don't see a single nitrogen ion. It's located next to these calcium ions, and then essentially we know it's there, right? Because we can probe it, and also because it displaces the calcium ion from the center of the trap, but you can't see it directly because it doesn't fluoresce. So the next step after we've prepared such an ion string is to sympathetically cool the molecular ion to the quantum mechanical motional ground state of the trap. So the ion traps that we use are harmonic traps, right? So in the quantum regime, you can think of them as quantum harmonic oscillators. And so we have different modes of motions of the ions in this trap, and we cool one of these modes of motion down to the 0-point energy level in the trap. So then, and here comes now the trick in terms of how we detect the quantum state of the molecular ions, we then apply a one-dimensional optical lattice. So 2 counter-propagating focused laser beams. And the point is that the wavelength of these laser beams is now near resonant with a strong spectroscopic transition in the molecule. So we typically use an electronic transition here, which is dipole allowed and therefore strong. We are not on resonant because then we would excite the molecule. We are only near resonant. And when we are near resonant, then what this optical lattice does is it produces a strong optical dipole force on the molecule. Yeah? It's a bit like an optical tweezer, if you like. And what we do then is that we modulate the frequency of this optical lattice at the frequency of the motional mode of the vibration of the 2 ions in the trap. So in this way, we grab the molecule with the optical dipole force, and then we start to shake it at its motional frequency in the trap. And that excites the joint motion of the ions in the trap. The 2 ions are coupled to one another by the Coulomb interaction. So their joint motion is then excited again, coherently excited by this modulated optical dipole force. And what we can then use is we can use the calcium ion as a thermometer, right? And by essentially doing Rabi spectroscopy on the calcium ion, determine by how much the 2 ions have been motionally heated up in the trap by the action of this optical dipole force. So we only see a heating up of these ions if the optical dipole force has been acting on the molecule. It only acts on the molecule if the molecule is in the correct quantum state, so that we are near resonant with a strong spectroscopic transition in the molecule. Yeah. And this is what gives us the state specificity in this whole scheme. Yeah. The molecule needs to be in the right state so that we have a strong optical dipole force, which leads to a heating, but it's not a heating, it's actually a coherent motional excitation of the 2 ions in the trap. Okay, so that is the general idea. Now let me walk you through the most important steps here in detail so that you see how it works. And the first step is the preparation of this calcium nitrogen 2 ion string. And that is actually something that is turns out to be more tricky than one would like to think. And this is now something for the ion trappers among you, which may be of interest to them. The problem is that we come in with a fast molecular beam, then we generate an ion, right? And when we generate the ion, it may gain additional kinetic energy in the potential of the trap. So sympathetically cooling a single fast ion by a single cold ion is hard. So what we do is we start with a big crystal, and then we produce one single molecular ion by our state selective photoionization, and this then sympathetically cools into the big calcium crystal. And you can see it here, right, as a defect in the calcium crystal. And then we successively eject calcium ions from the trap until a single calcium ion is left, and we are left over with a calcium nitrogen 2 ion string. And then we can do mass spectrometry, for instance, in the trap to ascertain that it's really a nitrogen ion that we have produced. So at this point, the secular temperature of these ions is on the order of millikelvin after Doppler laser cooling. So the next step is then to do cooling to the motional ground state, or to the ground state of at least one of the motional modes of this two-ion spring. And for that, we do resolved sideband cooling, so very standard technique in the world of ion trapping. So on the well-known calcium clock transition, so this is a transition from the 4s doublet as 1/2 state of calcium plus to the 3d doublet d 5/2 state of calcium plus. So we do the cooling on a specific Siemens component at the wavelength around 729 nanometers. And so what we do is we repeatedly excite red sidebands of this transition in order to reduce the motional quantum number until both ions have been cooled to the motional ground state of the trap. So that is so far pretty standard ion trap technology. What we then do as a next step is apply the optical lattice and produce the optical dipole force. And for this, I need to delve a bit more into the spectroscopy of N2+. So we now need to pick a strong spectroscopic transition in this molecule, which allows us to produce a strong dipole force. And what we do is we pick a vibronic component, so a specific vibrational transition in the electronic transition to the first excited electronic step. So we make an electronic transition at the same time we do a vibrational transition at the wavelength of around 780 nanometers. Yeah, and we've picked this particular transition just because of the wavelength, actually, right? Because 780 nanometers is a convenient wavelength. And on this transition, we have different spin rotational components. Yeah, so where we have changes between specific spin rotational states of the molecule, and these are shown here. Now, in particular, we also have transitions from the rotational ground state, denoted by the quantum number n equals 0 of the molecule. And that is in the end the one that we are interested in. So in these experiments, we've been preparing the molecule in the rotational ground state, and we wanted to detect that the molecule is really in the rotational ground state or some rotational excited state with our new scheme. Here on the left-hand side, you see a plot of the optical dipole force that's generated as a function of this lattice laser wavelength. And you can see here distinct features, right? Peaks in this optical dipole force, and they arise whenever the lattice laser is close to some of these transitions, right? In particular, this blue one here, which is a transition that originates from the rotational ground state. So meaning if we park the laser of our optical lattice, say at this wavelength here, right, which is very close to this transition that originates in the rotational ground state, then whenever the molecule is in the rotational ground state, we should experience a strong optical dipole force, and therefore a coherent motional excitation of the ion strip. And that is indeed what we observed here. So what we then do is, after we do this coherent motional excitation, we then do Rabi spectroscopy, again on the calcium clock transition. And so when no heating has occurred, then we operate the experiment in a way that we would then observe no Rabi flops on this transition. But when we have heating or coherent motional excitation, then we would see a distinct Rabi signal on the calcium clock transition. And from the Rabi frequency and also from the contrast of these Rabi flops, we can then work out by how much motional quanta the ion string has been heated. So we only see these Rabi flops when we had motional excitation, and we only have motional excitation if we had an optical dipole force, and we only have an optical dipole force when the molecule was in the right state. Yeah, so that is the rationale. So and here this blue trace is the signal that we get when the molecule was really in the rotational ground state. The green trace shows the situation that we get just in the background measurement if we don't apply an optical lattice, right? And and this green trace essentially reflects the background heating of the motion of the ions. And then one can also, play a game and put the molecule into a different rotational state, and then compare. And then try to do this motional excitation again, and then compare it with the situation when the molecule is in the right state. And that is this red trace here that one can see if the molecule is in an excited rotational state, then the signal that one gets essentially cannot be distinguished from background. Yeah. So this also shows that this is very sensitive to the specific rotational state that we have, and one can also quantify this a bit, do statistics on these measurements, and see with what sort of fidelity we can establish whether the molecule, whether the molecule is in the rotational ground state or some rotationally excited state. And what one can see here is that in the first series of measurements, the molecule was in the rotational ground state. And if you take all of them together, then we can work out a fidelity of 99% for the detection of this molecule in the rotational ground state. And then something interesting happened in this experiment. The molecule was actually changing its state, it was undergoing a quantum jump to a different state. And so we detected this immediately, and we could then detect also with a fidelity of about 99% that the molecule was no longer in the rotational ground state. So what has happened here was most probably a collision with a background gas molecule, and a rotational inelastic collision that has transferred this particular molecule in a different rotational state. So now one can use the state detection scheme now for spectroscopic measurements, and the very simple type of spectroscopy that one can do here is just map out these strong transitions that we used to generate the optical dipole force, right? Because the strength of the optical dipole force depends on the detuning from the resonance. So if we just detune the optical lattice closer or further to the specific resonance, we can then essentially map out the shape of this resonance. And this is shown here for the transition that we have been using to generate the optical dipole force when the molecule was in the rotational ground state. And these are transitions that have been very well known from conventional spectroscopy beforehand, and we can then compare the spectroscopic data that we get from our measurements with those previous measurements, for instance, line positions, and also quantitative information like Einstein A coefficients. And we get a very good agreement with the literature values, which gives us quite a high confidence that this scheme is also useful to extract really quantitative spectroscopic information. Okay, so what we are now gearing up to do is to apply this scheme again to do infrared spectroscopy or other types of spectroscopy on N2+, and now with a vastly improved sensitivity and therefore also precision. And to come back to the previous question, we've also worked hard to improve our quantum cascade laser in the meantime. So in the next step, we aim to do spectroscopic measurements with a resolution which are at least 3 to 4 orders of magnitude better than what we had before, and but the sort of precision that we will achieve in the end, and then also depends on the signal to noise, which remains to be seen. But one question that poses itself now: okay, which transitions should one really choose, right, in the future? Which transitions are really interesting? I've already said in the introduction that many of the systematic shifts that on rotation and vibrational transitions in nitrogen are very small, right? Black body radiation shifts are very small, DC Stark shifts are very small, quadrupole shifts are zero if you take the right transitions, all these sort of things. So but the thing that you need to be careful about are Siemens shifts. So the question is now, what sort of transitions can we find in this molecule, right? Which are only weakly sensitive to magnetic fields and therefore magnetic field fluctuations, and this is what impairs measurement precision in the end in this system. Okay, and as it turns out, the complexity of the energy level structure, right, is a big bonus here. Because one has so many energy levels and therefore so many transitions, right? And it turned out actually to be quite easy to find interesting candidates. So let me give you a few examples. One can think of just hyperfine transitions, right, in the radio frequency domain within, say, the I+2 nuclear spin isomer. And that here, that plot shows a prediction of the Siemens structure of these transitions that we get for the excitation from the F=3½ to the F=5½ hyperfine components in the rotational ground state. so what you see here is the transition frequencies for various of these transitions as a function of the magnetic field. And what one sees here is that already at rather moderate magnetic fields of a few tenths of Gauss, right, we have quite marked deviations from a linear Siemens shift. And the reason for this is interactions with other levels, yeah, because there are so many in the end of the day. And in particular, one can find magic conditions, as they are called, right, where the Siemens shift to first order at a specific magnetic field vanishes for this transition, right? And that is the conditions which are most or very attractive for precise measurements, right? Because here you can expect to have a very small influence of magnetic field fluctuations. So if one thinks of rotational transitions, right, for instance, a rotational excitation from the rotational ground state to the second excited rotational state, they are allowed, yeah, for instance, also by electric quadrupole coupling. And what one can see here is actually a quite interesting case if one looks at the hyperfine less nuclear spin isomer. And if one then looks at stretched Siemens transitions in this rotational transition, what one then finds here is that for these stretched transitions, so these states hardly couple to any other states in the molecule, and so they have a small but linear Siemens shift. Yeah, and so this is also quite interesting for spectroscopic studies because these transitions are, in other words, very well behaved. So then coming back to the rho vibrational transitions or vibrational transitions that we are primarily interested in, also here you can find various candidates for which you can realize magic conditions at specific magnetic fields where the influence of magnetic field fluctuations is expected to be very, very small. So in other words, you have a variety of clock transitions to pick from here in principle. And we will hopefully see soon in the experiment which one turns out to be the best. I should also say that by the same token, these transitions also make good qubits in the sense that this would constitute qubits with very good coherence times. Yeah, so there might also be interesting applications in the world of quantum science for these transitions. Okay, so to slowly wrap up, let me come to the last part of my talk. Another point is, of course, if one thinks of wanting to do very precise spectroscopic measurements on these molecules, then of course one also needs to be able to measure these frequencies very precisely. And so in the end of the day, what you would like is you would like to compare your measurements to some sort of very precise frequency standard, yeah, in order to get confidence in the precision of your results. And so ideally what we would like to do is you would like to compare your measurements to an atomic clock. And so we don't have one in Basel, but there is one at the Swiss Federal Institute of Metrology, METAS, in Bern. So they run or operate the Swiss primary frequency standard. It's a continuous cesium fountain clock, which also contributes to TIE and defines UTC for Switzerland. So what we have set up over the last few years is a fiber network, which allows us to transfer the signal from this primary frequency standard in Bern to our laboratory in Basel, and then onwards to laboratories at ETH in Zurich, and then back to Bern to close the loop, so that we can compare our measurements to this primary frequency standard in Bern. And this has been a large consortium of people, colleagues from ETH, METAS, SWITCH. This is the Swiss academic network provider. So essentially we use the academic telecom network to transfer the signal. And I should also point out, this is a collaboration with the Italian Metrology Institute, IMRIM, headed by the team of Davide Calonico and colleagues. So essentially what we do is so we have a telecom laser at METAS, which is stabilized to, in the end, to the primary frequency standard. This is then injected into the academic fiber network, and then we do fiber noise cancellation between matters and burn. And then we do regenerate the signal in Basel, and then we inject this regenerated signal into the network again, transfer it to Zurich. They then do the same, regenerate it, and then send it back to Bern so that we have a close a loop and then can do a round trip comparison, a round trip characterization of the whole signal. So of course, we are not the only ones here in Switzerland that have set up these sort of networks. There are now many similar types of frequency transfer networks all over the world, including Germany, Italy, France, and many other countries. However, what is a specialty of the Swiss network is that it operates at a very specific wavelength. So most other frequency transfer networks operate in the telecom C-band, because this is where most of where the hardware is optimized. But this is also at the same time where the data traffic operates. So one has to essentially share the bandwidth with the data traffic if one doesn't have dark fibers, and that introduces many complications. So what we did in Switzerland is we moved into the telecom L-band. So this is 30 nanometers away from the C-band, and at least in Switzerland, this band is completely empty within the academic data network. So we can do whatever we want there. And so we set up our entire hardware and the entire network to operate here in the L-band. And this gives us a lot of flexibility compared to many other implementations of this network all over the world. Okay, so what you see here is essentially a plot of the phase noise power spectral density as a function of the frequency that we get when we transmit the signal for the entire round trip, and with and without phase noise cancellation. And one can see that with phase noise cancellation, we achieve a much better performance than without phase noise cancellation. This is also exactly what one wants and what one expects. So to give you an idea how much this improves things for us, this shows an example measurement. So the 729 nanometer laser that we use to address the calcium clock transition. This is essentially the master laser in all our experiments. And this is the one that we then, in the end, lock to and discipline to the primary standard at Bern. And this here now shows the stability of the frequency, or the stability of this laser as a function of the averaging time in terms of the Ln deviation of the frequency, for the situation that we had before when we referenced it just to a local rubidium clock, which was disciplined by GPS. And here in red, you see the situation when we reference this laser now to the primary frequency standard. It matters, right? And already in the very first measurements that we did, we had an improvement on the order of 2 orders of magnitude, which is of course very nice. Okay, so now this infrastructure is now fully in place, also in Switzerland, and we are now using this routinely for our experiments and spectroscopic measurements in the lab. Okay, so with this, I'd like to wrap up. I hope I could have shown you a new method that one can use to non-destructively detect the states of molecular ions. It is quantum non-demolition and therefore highly sensitive, orders of magnitude sensitive than all the detection schemes that we have used before. And that means that it's a new approach to molecular ion spectroscopy, right, for which we have very great hopes. And as I've already said, I mean, it belongs to a family of new techniques that have been and are being developed by various groups all over the world at the moment, which I think really herald a new age for molecular ion spectroscopy, which we are very excited about. And the applications of this scheme that we can see are in precision spectroscopy, right? But what we also do in our group a lot is essentially collision physics and even chemistry. And I also see a lot of applications for this scheme there. And in the end, there may also be interesting applications in the wider realm of quantum technology, right? Because in the end, all the experimental toolbox that has been developed for atoms and atomic ions, and which is so successfully being employed in ion trap quantum information experiments, like the ones that are being done in Mainz and many other places, right? Essentially, we now have a very similar toolbox for molecules. And so I think molecules also can become very interesting in this context in the near future. So with that, let me thank the people who really did the work. So this is a photo of the current group. So that's the team who was and is working on this kind of experiments. Gregor Heggi is a PhD student who graduated last year. Sif Meir has been the senior postdoc on these experiments until recently. He has now moved on to a faculty position at the Weizmann Institute. Kaveh Nachafian was also a PhD student who graduated recently. Miko Rogushki and Alex Shlykov are current PhD student. Murid was a PhD student on the project and is now a postdoc. So those are the heroes behind the work, and I cannot acknowledge them enough for that. I also like to thank our collaborators on the frequency transfer project, our sponsors. And finally, I thank you very much for your kind attention, and I'm happy to take any questions if there are.
Thank you very much for this great talk and very exciting results. The talk is open for discussion.
Maybe I start with a question then. Yeah, super interesting and also very detailed, but in a good way, detailed talk about how your experiments are done. I was just wondering, because in the end you're looking for those nanohertz transitions, right?
Yeah.
Is this? I mean, well, first I was interested in how you're measuring the dipole force and whether it's trivial to show that the heating rate is proportional to the dipole force. I mean, in a way, hand-wavingly, I totally believe it, but I mean that it's linear. I probably also has like a dynamic range of forces that you can apply and those kind of things. Maybe you can comment a bit on this, and then of course that relates to the question on how to extend this to those nanohertz transitions.
Yeah, that is a very good question. Yeah, so what I've shown here is this is something that we calculated. Yeah. And of course, one needs to measure this in the end. And in order to accurately measure this in the experiment, we actually compare it to a reference dipole force that we apply on the calcium ion. Because in the calcium ion, you can determine and measure this much more accurately. What we effectively do is we measure the AC stark shift on the calcium clock transition. And from that, we can determine very precisely optical dipole forces, right, that act on the calcium ion. Yeah, and we can then use these measurements to compare them with the measurements on nitrogen. Yeah, because it's the same two ion string in the end that is heated in the day in this way. So this is how we actually measure the dipole forces on the nitrogen ion, and that this works very well. That can be seen here from these measurements, yeah, because here we really extract quantitative information from these dipole forces. So this is essentially the dipole force, right, as a function of the detuning. Yeah, and that here is the Einstein A coefficients, right? So essentially transition strengths, right, which determine the strength of this dipole force, right, that we extract from these measurements, right? And we can, from our experimental protocol, we get a value which we can compare with the literature, and the literature values are these dashed lines here, right? And one can see that the agreement is really very good. Yeah, so it's a bit involved, yeah, to determine really the strength of these dipole forces, but it works quite well in the end. So coming to the question about this 10 nanohertz, yeah, I mean the 10 nanohertz, this is technologically not feasible at the moment. Yeah, and in the next step, we hope to be able to measure these transitions with a precision on the order of hertz or tens of hertz. Yeah, so that is the next step. So that is what. So we've now considerably improved our quantum cascade laser in terms of line width, which is a project in itself in this wavelength range. So and this is now a line width on the order of kilohertz or better. So with that, I think if we have a good signal to noise, then we can really hope to get a position on these line positions on the order of say 10 Hertz or so.
Okay, any further questions?
Dima Butker clearly is jet-lagged.
It was a fantastic talk, really, really interesting.
Okay, thank you very much, Dima.
Thank you. Yeah.
Well, maybe I have one. You showed the example of nitrogen molecule. Do you have other examples that you anticipate, or you stick on that one?
Yeah, so nitrogen is our pet molecule, which we have chosen essentially because it's not polar. Yeah, and so this is why it has all these narrow transitions. But of course, there are many other molecules that you can think of. Yeah, and Pete Schmidt at PTV, for instance, has started working on O2+. Yeah, which is a very similar system, which is attractive for the same reasons, right? It's an apolar diatomic ion. At NIST, they work on calcium hydride plus. Yeah, so there are many different systems you can choose. Yeah, and in the end, it really depends on what kind of questions and properties you are interested in. I mean, one foreseeable next step is of course to go to polyatomics. Yeah, and then really, I mean, the whole chemical diversity of molecules becomes available to you, right?
Mm-hmm. Okay, thanks. Are there further questions? Yeah.
Well, maybe not a question, but maybe something that you may or may not be aware about is that we here in Dima's group are looking for dark matter in various ways. And in particular, we are looking with networks of optical magnetometers. I mean, we have like a lot of magnetometers all over the world, and they are, then we measure basically dark matter that looks like a transient magnetic field. And for quite some time now, we are also, and there's also a slightly different branch of, it's not of our group, but of like collaborators, if you want. They're doing this with optical clocks of networks of optical clocks used to exclude dark matter. They started with the satellite clocks on the GPS system, and now we, at least here in Mainz, are trying to push that also to optical clocks, even though we have no.
That's fantastic. Yeah.
But yeah, have you ever considered using your networks to, or would you be interested in joining such a network? I mean, then the question would be how to get your data and how fast your sampling rate would be, and so on, and what kind of data we could actually use.
Yeah, I mean, I think that it would be an extremely fascinating perspective. Yeah, and yeah, one would have to look into more detail how molecules could maybe contribute to that. I mean, I think in terms of experimental uptime and duty cycle, right? I mean, we're still a bit experimental here and not right at the stage with which you could maybe run an ytterbium optical clock or something like that. Yeah, but well, I hope that in the very near future this is sorted, and then I think molecules may indeed become also be interesting in that context. I think one would look a bit deeper into that.
Maybe there are particular dark matter models, and I'm sure Dima has an idea of this, that are where just molecules would be sensitive to, for example. I mean, maybe this can be envisioned. Dima, what do you think?
We have a paper in collaboration with Stefan Schiller's group.
Okay.
On the search for relatively fast oscillation of fundamental constants.
All right.
But we use more classical kinds of spectroscopy, so we can look for variation frequencies up to 100 megahertz. And so that was actually my question I wanted to ask, like in the far future, how can you potentially read out the molecular frequency molecular frequency, sort of fast variations of molecular frequencies? Is there some way to do this?
So if the transition frequencies changes very fast.
Yeah, so it's oscillating very fast because alpha, instead of slowly drifting, it just goes back and forth. And that would be a result of, well, this happens in some dark matter models, where dark matter is the background field, and it could be oscillating and changing the fundamental constants.
So it would really be about very fast measurements.
So I guess one would just probably need to reconfigure it, not really as a precise clock that takes measurements very infrequently, but some kind of a dedicated experiment. But molecules are great because they're sensitive, for example, much more to variation of nuclear mass or strong interactions or something like that.
Yeah. I mean, this should also then essentially be reflected in the coherence properties of these transitions, right? If they change very fast. Yeah, and I guess that would then be the way to measure it, right? So say if you you don't agree?
I'm not sure. I'm not maybe I don't see that immediately, but it's more like there appears some kind of sidebands in energy, if you want,
Okay. Yeah.
So that would be something like that. In addition, potentially to having the main transitions, you would have satellites at some at the dark matter, for example. Yeah, something like that.
So it's a really strong modulation.
No. No, it's a small modulation index, high frequency, right? So it would be very, very small sideband.
Right.
Well, let's say you have your line, and then away from it is a tiny copy, right, on the left and on the right, or something like this. Yeah.
Okay.
So maybe it's in I don't know, a direction to think about.
Yeah. I need to think about this. I will look up your paper.
Thanks.
What sort of molecule did you consider there? What's this?
We have a paper on iodine.
On
iodine.
Iodine.
Yeah.
Okay. So a heavy. Okay.
Well, it just be Maybe a light molecule could. I have to think a bit. Maybe light molecule could even be better for this.
Was there a specific reason for choosing iodine?
I think it's just convenient molecule to have in a vapor, and Stefan Schiller also has worked with iodine for a long time, and so we did two experiments, one in our lab and another frequency range in Stefan Schiller's lab.
Yeah, that's true. I mean, iodine has transitions everywhere in the optical. Yeah. I can see the appeal, at least from an experimental side. Yeah. Thank you very much for this comment and this suggestion. I need to think about this a bit, and I will look up this paper. Is this a recent one or?
Yeah, it's we have one paper in quantum science and technology, and then one on the archive. I don't think it's published yet. Yeah.
Okay.
But it's on the archive.
Okay. Thank you very much.
Yeah, but regarding the network, we also published something this year about the magnetometer network. That's in Nature Physics, which I can post a link to. But this is sort of a different schematic.
Yeah, I will put the reference with Stefan in the chat in a second.
Okay, very good. Thank you.
Can I please also make a comment or ask a question, maybe sort of piggybacking off Arne and Dima's remarks about dark matter? So there are also alternative ideas, such as modified Newtonian gravity. I've always wondered if you could probe this with molecules as well, where you could imagine, well, yeah, you have your two masses, and as long as you know how to describe the electromagnetic interaction well enough, at some point you will also become sensitive to gravitational attraction between the nuclei.
Mm-hmm.
Are there any people working on this? Are you? Do you have any ideas about this?
So, I mean, the people in Amsterdam, for instance, Wim and colleagues, right? I mean, they have, it's not exactly the same as you're talking about, right? But they have been looking into the possibility of exploring fifth forces with molecules.
Right, yeah.
And things like that. I'm not aware that anyone is looking into gravitational effects at the moment.
So I can just comment that in terms of MOND, the presence of the large Earth acceleration is a problem in many frameworks. For instance, you know, the sorry, I'm jet lagged now. I'm of course blanking on the name of the great founder of MOND who came to our group meeting and sorry. But he said,
I think his name also started with an M, right? Some people call it.
Yes. Just a second, I'll remember it. But the point is that he's very skeptical of any test in the presence of gravitational acceleration. But that doesn't stop other people. And there's one enthusiast, Pavel Faddeev, in our group who pushes on those also. So thank you, Arnim. It's Moti Milgram, right? Yeah. Yeah, thanks.
Yeah.
Okay.
I think as a general point, right? I mean, what you have, what molecules offer in addition to atoms, right? I mean, are essentially rotational and vibrational degrees of freedom, right? Which, you know, strongly depend on nuclear masses and associated properties, right?
Well, simple molecules also offer they are among this, as I don't need to tell you, of course, because it was on your first slide, I think, that the molecule like HD, for example, can be calculated precisely. And so there are great systems to look for exotic spin-spin interactions, for example.
Yeah.
In fact, there is a puzzle about, I think, spin-spin interaction in hydrogen isotopes, HD, DT, and you know, all the combinations.
Which at the same time raises a general problem, right? Because I mean, for HD plus and H2 plus, right? I mean, one can do very precise calculations, right? But as soon as you add only a single additional electron, right? I mean, things become much more difficult, right? And that is, I think, on the theory side, this is one of the main challenges, right? That also for, I mean, when it comes to a molecule, N2 plus, right, is not a very complex molecule, yeah, for a chemist at least. But for precise theory, right, this molecule is a nightmare. And and this is one of the areas where I think a lot of progress is needed in the near future, right? So that we learn to tackle the theory of these molecules much better than we do at the moment.
Can I ask you another question about molecules? I think we have a few more minutes, right? Do you have any way of fixing the axis of the molecule inside your trap? Or is it fixed?
That would be a dream.
You mean, do you mean applying electric field?
Orient them.
Yeah. Oh, yeah, orient.
That's what you mean. Yeah, yes. Or align them. Yeah.
Yes.
No, not easily. I mean, we do in other parts of my group, we do experiments with orienting molecules and stuff like that. But in an ion trap experiment, you can't apply a strong electric field, right? I mean, this would in nitrogen, this wouldn't work anyway because it's apolar, right? But with a polar ion, you could think of doing that. But of course, then your ion trap doesn't work anymore. You can do alignment experiments with ultra short laser pulses, of course, right? That is something that would work, but the time scales are not really commensurate, right? I mean, with a short laser pulse, you can align a molecule for a very short amount of time, right? Typically femtoseconds, and or picoseconds, right? Depending on the system. But you know, our experiments, they span over minutes, if not hours, right? So yeah, it's not easy. It's not. It would be a dream to be able to do that, yeah. But I'm not seeing it in a straightforward way at the moment.
Right.
All right. Are there further comments or questions? Yeah, if it seems not to be the case, before closing the session, let me first check which is the speaker for next week. Okay, next week we'll have Professor James Thompson from GILA. He will then talk to us about experiments in many-body cavity QED. Yeah, thank you.
Who was that from GILA?
James Thompson, right?
Oh, James Thompson, fantastic.